Hello friends, welcome you all to the 10th lecture on function analysis and its applications. In this lecture, we will discuss on the linear space LP and L infinity as Banach spaces. Following contents are the today's lecture. The space LP as Banach space and the space L infinity as Banach space. The space LP. Let P belongs to 1 to infinity, that is 1 less or equal to P less than infinity, and let LP denote the space of all sequences as x is equal to x1, x2 and so on, infinite dimensional, of such scalars such that summation n is equal to 1 to infinity mod xn power p less than infinity, that is sum of the infinite series should be bounded, because here x is infinite dimensional, x1, x2 and so on, then series will be finite, convergent series. Then LP is Banach space under the norm x over p defined as summation n is equal to 1 to infinity mod xn power p whole power 1 by p. In previous lecture, we have discussed the spaces LPn and L infinity n. Here n, okay, vector x as n tuples x1, x2 and so on xn. But here infinite dimensional, so sequences x1, x2 and so on up to infinity. Okay, so this is all sequences as up to infinity, then summation of the all sequences with power p should be convergent. So this is the requirement of this example. Okay, and norm I earlier defined summation n is equal to 1 to infinity here. In that case, LPn, here summation I is equal to 1 to n mod xi power p whole power 1 by p. But here in infinite dimensional case, norm defined summation n is equal to 1 to infinity mod xn power p whole power 1 by p. Okay, let us prove. First, it is a non-linear space and then completeness. So, here we have taken two sequences as x is equal to x1, x2 and so on, and y is equal to y1, y2 and so on belonging to LP, not LPn. Here it should be only LP. And alpha be any scalar, then x plus y equal to x1 plus y1, x2 plus y2 and so on. And alpha x can be defined as alpha x is equal to alpha x1, alpha x2 and so on. We now first show that LP is nonlinear space. Since mapping norm this from space LP to R and norm x over p defined as summation n is equal to 1 to infinity mod xn power p whole power 1 by p is norm on LP. It follows the following properties. Since here summation mod xn power p, and we know that modulus value of any point xn always non-negative, that is mod xn greater or equal to 0, and here norm defined summation of mod xn power p from n is equal to 1 to infinity, that is also greater or equal to 0. Hence, we can say that norm xp greater or equal to 0. First condition satisfied. Second, if norm xp is equal to 0, if and only if norm xp defined this summation n is equal to 1 to infinity mod xn power p whole power 1 by p. So it is defined here. Since norm xp is equal to 0, then this is equal to 0. If and only if taking the pth power of this equation, so summation n is equal to 1 to infinity mod xn power p is equal to 0. This is the modulus value. So only one possibility that mod xn is equal to 0. Mod xn is equal to 0, it means xn is equal to 0 because here modulus value. Okay, so xn is equal to 0, it means x1, x2 and so on xn, each n all 0, that is x is equal to 0. Third, for a be any scalar, then we have norm axp. So ax, if x defined as x1, x2 and so on, then alpha x is equal to alpha x1, alpha x2 and so on. Then norm alpha x over p norm, we can define summation n is equal to 1 to infinity mod axn power p whole power 1 by p. Okay, so a free from n, so we can write outside the summation. So this is mod a power p summation n is equal to 1 to infinity mod xn power p whole power 1 by p. That is mod a power p whole power 1 by p, that is mod a, and summation n is equal to 1 to infinity mod xn power p whole power 1 by p. So as per the statement, we can write this norm xp. Hence, norm a xp is equal to mod a norm x. Fourth condition, if x is equal to xn, n is equal to 1 to k and y is equal to yn, n is equal to 1 to k are two elements of LP k, then by Minkowski inequality we have norm x plus y p equal to summation n is equal to 1 to k mod xn plus yn power p whole power 1 by p. This is less or equal to summation n is equal to 1 to k mod xn power p whole power 1 by p plus summation n is equal to 1 to k mod yn power p whole power 1 by p. Okay, so norm x plus y p less or equal to norm xp plus norm yp when x is equal to xn, n is equal to 1 to k, finite dimensional. Okay, but if we extend as limit k tend to infinity, okay, then here k tend to infinity, then x is equal to xn, n is equal to 1 to infinity and y is equal to yn, n is equal to 1 to infinity. Then Minkowski inequality can be defined as norm x plus y under pth norm is equal to n is equal to 1 to infinity mod xn plus yn power p whole power 1 by p. That is less or equal to summation n is equal to 1 to infinity mod xn power p whole power 1 by p plus summation n is equal to 1 to infinity mod yn power p whole power 1 by p. Here we have taken k tend to infinity. Okay, consequently, ELP is a nonlinear space because all four conditions of nonlinear space satisfied. Hence, LP is a nonlinear space. Now, we prove the completeness of LP. Let XM be a Cauchy sequence in LP, where M is equal to 1 to infinity. And XM has infinite dimensional, that is XM is equal to XM1, XM2 and so on up to infinity. Okay, such that the all sequences satisfies the summation of infinite series, that is infinite series will be convergent. Okay, that is summation n is equal to 1 to infinity mod xm n power p less than infinity, because here already if x has infinite dimensional sequences, then we have the series this. Here we have defined Cauchy sequence xm has infinite dimensional xm1, xm2 and so on. Then as per the statement, it should be also n is equal to 1 to infinity mod xm n power p less than infinity. So as per the definition of the Cauchy sequence, let epsilon greater than 0, there exists a positive integer n, and depending on epsilon, such that norm xmn minus xln under pth norm less than epsilon for m l greater or equal to n epsilon. As per the definition or statement of the example, we can define the norm xmn minus xln less than epsilon as summation n is equal to 1 to infinity mod xmn minus xln power p whole power 1 by p less than epsilon. Okay, taking the pth power of both sides, this implies that summation n is equal to 1 to infinity mod xmn minus xln power p less than epsilon power p. Okay, it has the infinite term. Okay, so sum of the infinite term less than epsilon power p. It means as individual mod xm n minus xl n power p less than epsilon power p. Okay, taking the pth root of both sides, then this one, that is here we have this, it has infinite number of terms less than epsilon power p. It means as individual each term x m n minus x l n power p less than epsilon power p. Taking pth root of both sides, we get this one. Okay, for fixed n, xln is a Cauchy sequence in RRC, that is as individual xmn and xln as scalar. Okay, it belongs to RRC, and we know that R and C being complete. So each one of them, the sequence xln converges to the point xn as L tend to infinity. Okay, because RRC being complete. Then we claim that xm Cauchy sequence, here we have taken xm, so we claim that xm, m is equal to 1 to infinity. Okay, here it should be m. Converges to the point x, that is xn, x is equal to x1, x2 and so on up to infinity. Okay, so here in short way we can write xn, n is equal to 1 to infinity. So we claim that xm converges to the point x. This one. Now from equation 2 and 3, here equation 2, this one, and 3, xln converges to the point xn. So this xln converges to the point xn as L tend to infinity. So from equation 2 and 3, summation n is equal to 1 to infinity mod xm n minus xn power p less than epsilon power p. Okay, putting the value of this. So as per the statement of norm, take the pth root of this inequality. We have summation n is equal to 1 to infinity mod xm n minus xn power p whole power 1 by p less than epsilon. As per the definition of p norm, this implies that norm xm minus x less than epsilon for all m greater or equal to positive integer n. Meaning of this is xm converges to the point x as m tend to infinity. Okay, this shows that xm converges to x, where x, x1, x2 and so on. Now we have to prove x is the element of LP. Okay, as per statement of the example, here if x is equal to this one, then we have to check this condition. Okay, so here xm converges to the point x, then now we have to check x belonging to LP. Since mod xn power p equal to mod xn minus xmn plus xmn power p. We have added xmn and subtracted xmn. Okay. This inequality can be written as less or equal to 2 to the power p. Okay, here p, 2 to the power p xn minus xmn power p plus xmn power p. This inequality can be written as this one. How to write? Suppose two numbers a and b, then modulus of a plus b power p less or equal to pth power of modulus a plus modulus b. Okay, here two numbers a and b, so one may be greater or equal to another. So we can write this is less or equal to 2 max value of a or b whole power p. Okay, so 2 to the power p and max value of mod a mod b power p. Okay, so any one maximum value, so we can add any value that is less or equal. So we can write mod a plus b power p less or equal to 2 to the power p mod a to the power p plus mod b power p. So mod xn power p less or equal to 2 to the power p mod xn minus xmn power p plus mod xmn power p. Now taking the summation from n is equal to 1 to infinity both sides of equation 5 we have here mod xn power p taking the summation of both sides from n is equal to 1 to infinity. So we have summation n is equal to 1 to infinity mod xn power p less or equal to 2 to the power p summation mod xn minus xmn power p, that is this, plus 2 to the power p summation n is equal to 1 to infinity mod xmn power p, that is this one. So using equation 2 and equation 1, okay, this one and this one, this is less than epsilon power p. Why? Because here equation 2 summation n is equal to 1 to infinity mod xmn minus xln power p less than epsilon power p, and here xln converges to the point xn, then here xn. So we have the value of this one epsilon power p, and again from 1 summation mod xmn power p less than infinity, then we have here bounded by any positive number. So this total summation less than infinity. So summation mod xn power p less than infinity. Okay. So we can say that x is equal to x1, x2 and so on xn such that it satisfied mod xn power p less than infinity. So we can say that x belonging to LP. Thus every Cauchy sequence in LP converges to a point in LP. Hence LP is a complete normed linear space, that is, it is a Banach space. Example 2. The space L infinity. L infinity is the set of all bounded sequences x is equal to x1, x2 and so on mod xn less than infinity of scalars with norm x under infinity norm defined supremum n belonging to 1 to infinity, n is equal to 1, 2 and so on up to infinity. For all x belonging to L infinity is a norm on L infinity and it is a Banach space. Okay. Already we have discussed in previous lecture L infinity n as a Banach space where x is equal to x1, x2 and so on xn in L infinity n. Okay, that is finite dimensional. Okay, here in finite dimensional case, okay, all bounded sequences of scalars. Okay, since here in finite dimension, then mod xn less than infinity, that is mod xn bounded sequence. Okay, mod xn less than infinity or supremum of mod xn less than infinity. Now we prove first L infinity as normed linear space. Okay, and then completeness. So here mapping norm such that L infinity to R and norm defined x infinity is equal to supremum 1 less or equal to n less than infinity mod xn. So now we check the all conditions of normal linear spaces. Okay. Since mod xn greater or equal to 0 and norm here defined supremum of mod xn, so it will be also greater or equal to 0 because this norm depends on the mod xn. Second condition, norm x equal to supremum mod xn equal to 0. If and only if mod xn equal to 0 for all n. Okay. So here modulus value. So xn is equal to 0 for all n, that is each term 0. Okay. That is x is equal to 0, 0 and so on up to infinity. That is 0. Okay. So norm x is equal to 0 if and only if x is equal to 0. Third condition, for any scalar a, we have norm ax defined as supremum mod axn. Okay, because if x is equal to x1, x2 and so on, then alpha x is equal to alpha x1, alpha x2 and so on. So norm ax can be written as mod axn equal to supremum of mod a mod xn. Here mod a free from n, so we can write the mod a before of the supremum mod xn. So supremum mod xn can be written as norm x. So norm ax equal to mod a norm x. Fourth condition, if x is equal to xn, n is equal to 1 to infinity and y is equal to yn, n is equal to 1 to infinity are two elements of L infinity, then we have norm x plus y infinity is equal to supremum of mod xn plus yn as per the definition, because x is equal to x1, x2 and so on, x I and so on up to infinity, and y is equal to y1, y2 and so on, yi and so on infinity. Then x plus y equal to x1 plus y1, x2 plus y2 and so on up to infinity. Then norm x plus y supremum of nth term of x plus y. Okay. So this can be written as mod xn plus yn. Okay. So norm x plus y less or equal to supremum of mod xn plus mod yn. This is also less or equal to supremum value of mod xn plus supremum value of mod yn. That is norm x plus y less or equal to norm x plus norm y. This shows that L infinity is a nonlinear space because all conditions of nonlinear space are satisfied. Completeness of L infinity. Let xm m is equal to 1 to infinity be a Cauchy sequence in L infinity since each axiom has infinite dimensional points, so axiom has axiom 1, axiom 2 and so on, such that axiom n less than infinity as per statement defined here. If here x infinite dimensional, then mod xn less than infinity. So we have taken Cauchy sequence xmn, xm has infinite dimensional, so xm1, xm2 and so on, then mod xmn less than infinity for all n. N lies between 1 to infinity. Let epsilon greater than 0, there exists a positive integer n epsilon such that norm xm minus xl less than epsilon for all ml greater or equal to n epsilon. This implies that as per the definition of norm in L infinity, supremum of mod xm n minus xl n less than epsilon. Here supremum value less than epsilon, it means xm n minus xl n less than epsilon for each fixed n. Okay. Thus, for fixed n, xm n is a Cauchy sequence in RRC. And also we know that R or C being complete, each one of them converges to some number R or C. That is here sequence xmn minus xln. Okay. So each one of them converges to the some number in R or C. So xln suppose converges to the point xn as L tend to infinity. Okay, where x, that is xn, n is equal to 1 to infinity, x1, x2 and so on to infinity. Okay, so we claim that xm converges to the point x. Now from equation 7 and 8 we have here 7 mod xmn minus xln less than epsilon and xln converges to the point xn. Okay, so we can write supremum mod xmn minus xn less than epsilon. Okay, as per the definition of L infinity norm, we can write supremum of xmn minus xn as norm xm minus x infinity norm less than epsilon. As per the definition of the convergence in nonlinear space, we can say that xm converges to the point x. This shows that xm converges to x, where x is equal to x1, x2 and so on. Now we show that x belonging to L infinity. Okay. In the statement here written, if x this one, then mod xn less than infinity. So here we see that the sequence xn converges to the point x, x is equal to x1, x2 and so on up to infinity. Then now we have to check x belonging to L infinity. That is, we have to check mod xn less than infinity. Since mod xn can be written as mod xn minus xmn plus xmn. Okay. We have added xmn and subtracted xmn. So this can be written as less or equal to xn minus xmn plus mod xmn. Now using equation 6 and 8, here xln converges to the point xn, then we have this mod xm minus x less than epsilon. Okay, this one. Since supremum of 1 less or equal to n less than infinity mod xmn minus xn less than epsilon, so mod xmn minus xn also less than epsilon. So using this, value of this one is less than epsilon, and mod xmn from equation 6. Okay, then this is less than infinity bounded by some positive number, that is k. It means mod xn less than epsilon plus k, that is total less than infinity, that is mod xn is bounded. Hence we can say that x is the element of L infinity. This shows that xn n is equal to 1 to infinity, that is x belonging to L infinity. Thus, every Cauchy sequence in L infinity converges to a point in L infinity. Hence, L infinity is complete normed linear space, that is, it is a Banach space. C space, this is similar to the L infinity space. So this is a space of all convergent sequences x of complex number with the norm defined by norm x supremum k xk. Hence C is Banach space. Proof is similar as above example second. Similarly, C0 space, this is the space of all sequences of complex numbers which converges to 0 with the norm defined by this. Okay, here converges to the point 0. This is norm also defined as example 2. Okay, so we have avoided to prove in detail here. Okay, here also proof. In this lecture, we have discussed the spaces LP and L infinity as Banach spaces. We have used the following references in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Narisi. Function analysis with application, John Whaley and Sons, written by Erwin Krejcik. Next, function analysis, New Age International Publisher, written by V.V. Lemieux, and function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you for your attention.